here and there when I point to it. But we need some vocabulary. See, if we take some vocabulary and, for example, name these first 2 points that started all of this. We'll name the first one A and the second one B. And if we do that, and I'm in charge, and I suggest we do that, then we don't have to say here and there. We can say that there's a green circle centered on the A point, and there's a green circle centered on the B point. There's also a black circle centered on the A point, and a black circle centered on the B point. Then we can enlarge our vocabulary about relationship and connectedness of things to say that, well, the green circle and the black circle centered at A share the same center. So we can decide that we will create the word concentric for that. And concentric is just whatever word we choose to represent this relationship. So it's not concentric. Concentric is just the map, not the territory, so to speak. See? So now we've got a pair of circles centered at A, a green one and a black one, and a pair of circles centered at B, a green one and a black one. And now I'm going to draw, and let me mark in green for you the points that I used to choose my diameter. That's the point I chose here. This is the point I chose to draw the green circle centered at A. And that circle also passed through a point similarly down below here. And for the green circle centered at B, the point that I chose is that and that. Now this is just leaving a trail, and it's not something that you should try to remember, because I don't think you should try to remember what I'm saying. Let it happen, and you are owed to hear this more over and over again. Now I'm going to draw a couple of blue circles. What I'm doing is handed down from more than 2,000 years, and this is how it's done. And the first time you see it, you have nothing more than to sit back and take it. Now I'm going to draw a blue circle centered at A because of the point that I made here with that green line. And that's why I drew the green line, to create this point so that I could draw a circle of that radius and a circle on the other green line, a circle centered at B of that radius. Now, why I picked that up? Because these 2 points provide a square above my original. That is a unit square. That is a square of this same size. Because this is the shared radius, this is the same radius, this is the same radius. And you'll have to guess that these lines, the 2 green lines, have a relationship that is parallel. We don't know that, but I can announce now the word parallel, and we can spend the rest of our lives seeing if that's plausible. But I have announced that the 2 green lines are parallel. I have announced that the green lines are perpendicular to the black line, and this and only this is the meaning of parallel and perpendicularity. Now, these are a couple of terms, parallel and perpendicular, that lose their meaning when your geometry ceases to be plane geometry. When the geometry is spherical, the geometry of the surface of the Earth, for example, there is you're in great difficulty talking about what's parallel and what's perpendicular. this was the, the impetus for the entrance into relativistic fourth dimension non-Euclidean geometries, the predicament of the parallel. But we are in the plane, and we see what parallel means from the beginning. So this is from the blank page. Now I want to draw those blue circles. That, see, the blue circle and the radius, is it clear to those, to my partners here, that this is a square?
Yes.
Above. Mm-hmm. And as above, so what do you call it?
Below.
Yeah. So there's a as above, what's the name? I don't want to blame, I don't want to come out of the closet with weird vocabulary. So that's why I needed the green lines. And that's why I needed the 4 extra circles. See? And I knew that. I knew that I needed to draw the 4 extra circles, this one, this one, this one, and this one, so that I could create that point, and that point, and that point, and that point, so that I could draw the green lines, so that I have the green line strike the A circle here and the B circle there, above and below, and develop for myself a square above and a square below. And those let me draw the two circles. Those are forms that we could discuss at length forever, but we won't. I just want to finish, construct a diagram here. Let's see if I can do this. What I want to do is draw. I want to draw a couple of blue circles. Now there is a blue circle centered at A. I'm going to draw a blue circle centered at B, and then I want to draw some more circles, but I want to find a scheme for having the circles centered at A of a different color than the circles centered at B, so that we can, when we look at them, we can backtrack and unfold some of the complexity of this pattern. Because this is the pattern that is going to be the basis for defining some numbers other than these. See? Now we remember how we defined these numbers by that. And we need all of this complexity to define numbers that require the circle explicitly in defining what the number is. See? So that's what we're doing. I have already set up here so that the numbers that we define, that we can count, are going to be the radii of the circles centered at A and the radii of the circles centered at B. And we see here's the radius of the black circle centered at A. We've got 3 circles centered at A. This is the radius of the black circle. This is the radius of the blue circle. And it's the second circle. And this is certainly not 2 times that. And this is the radius of the third circle. And it's not 3 times that. So that we can say that we are replicating this first circle to a scale that is funny. It is certainly not linear. and we're going to use the radius of that family of circles as the definition of number. So we're not going to call this number 1. We're going to call this number the square root of 1. And what do we gain by that? And then we say, well, what the heck is 1? Well, what do you mean by square root of 1? Square root of 1 is whatever you multiply by itself to give you 1. So 1 will be square root of 1 times square root of 1. And we'll call that an area. So we'll say that the side of this square is the square root of 1, and the area is 1. So we have split the 1. And this, conceptually, intellectually, and in terms of the foundation of mathematics, this is as significant as splitting the atom. Because it is we who decide in mathematics what the unit is. What's the thing in terms of which we count everything else. So we will say the first circle, by definition, is radius square root of 1. And then this area times this length is that area. And that unit square is 1. And so we no longer have the case that square root of 1 equals 1. See, this is dimensionally defective. And this is a dimensional defect that we have gotten along with in Western mathematics since we became disturbed by recognizing that the diagonal of the unit square is the square root of 2. This is square root of 2. So we've got square root of 1 as the radius of the first circle. Square root of 2 is the diagonal of the unit square. And square root of 3 is the radius of this green circle. Now, I'm just saying that, and I'm not going to stop for us to prove it, because we don't need to prove. Either I'm lying or made it up, but I'm making a sweep, and we need to sweep beyond that and leave this as an exercise for the mathematicians to establish that this is or is not, this radius of this third circle is or is not square root of 3. See, we're leaving that as an exercise for the mathematician expresses my understanding of my relationship as a scientist to the non-scientist. We are servants of meaning that is a reduction from the ineffable. We have perceptions that we have to make reductive conceptions of. And this, the role of science, which means in the word knowing, is to help us